if you'll remember the 5 themes from the very beginning. So the first section was on the spherical Coxeter groups. Second section was on Euclidean Coxeter groups. Third section was supposed to introduce general Coxeter groups, and you've now seen a definition. It's just by presentation. You write down a diagram, you have a presentation. And at the moment, I've told you a couple of basic facts about the presentation. I told you how to solve the word problem, but I haven't told you why that works. And so the fourth section is about linear representations. And so when I say section 4, linear representations, or let's say, let's be more specific, a very special linear representation and how to prove some basic facts. And let's talk about what I mean by that. So a very special linear representation and how to prove some basic facts. So what is a linear representation, first off? So a linear representation means that you have a group homomorphism from your group G to GLNV. GLNR or GV. V is a vector space. And this is the general linear group. Of all invertible linear transformations V to V. So it's basically a way of taking your group and trying to understand a bit about its structure by mapping it over to a collection of matrices, a collection of linear transformations, so that all of the relations in the group hold over here. It may or may not be an injection, right? It may or may not be an injection, but if you can find, and so this is called a representation, this group homomorphism. This group homomorphism is called a representation because you're turning your group elements into linear transformations. You're turning your group into study of your group into study of linear algebra. And what you would hope for, what would be ideal, is if you can find an injective group homomorphism, if you can find what's called a faithful group representation. Because if it's faithful, then you can actually completely understand your group. Because all you do is you take the elements, you turn them into the matrices, and if you have a word, you multiply the matrices and you just check whether you get the identity matrix. Right? So, where we want to be by the end of the hour is I would like to describe how to take an arbitrary Coxeter group, and for every Coxeter group there is a very particular group homomorphism over into matrices. Okay? So that's where I want to end up. Where I want to start is I want to start with some examples. I want to start with some very, very simple examples. And the first example that I want to do, so I should say, what are the basic facts that we want to do? So at the moment, I've told you how to do the word problem. Another thing that I haven't told you how to do, but is something that you might wonder, is the following. If gamma is, let me just write some small diagram. Let's call this A, B, C, and D. And maybe I can just ask for some integers. Give me some large integers. Just name some numbers. I want to put numbers on there, but I don't want to be responsible.
29.
29, okay. How about some that aren't prime? Google? Okay. Like 10 to the, what is that, 100? Okay. How about some smaller ones? 11, okay. Three more. One. Ooh, that's bigger than one. Bigger than one. Because if we said 1, then what would that say? That would say that AC equals 1. AC to the 1 equals the identity. That ends up saying that A equals C inverse. And since C and C inverse are the same, it says A equals C. And it actually, yeah. So one's not, one, if there was a 1, we could actually just collapse A and C. All right? How about like 12, 200, and 14? Okay? So this corresponds to a presentation of a group, right? We've got A, B, C, D. A squared equals B squared equals C squared equals D squared equals 1. And what do we have? We have AB to the 29th equals 1. We have AC to the 12th equals 1. AD to the 11th equals 1. BC, what was the number there? 200 equals 1. BD to the Google equals 1. And CD to the 14th equals 1. Right? So, does this mean, so this defines a group, right? This definitely defines a group. But you might not, there are some questions that we don't know. For example, what is the order of BC? What's the smallest power of BC that's equal to 1? Right? I take BC, BC squared, BC cubed, B to the 4th. I know that when I get to the 200th power, I get the identity. But it could happen earlier. Right? It could be that BC to the 5th is equal to 1. That could be a consequence of all these relations. In some complicated way, there could be some, I could be able to prove from these relations that BC to the 5th is equal to 1. It seems unlikely, but it's possible. So what we know, that in this case, the order of BC, what do we know? We know that the order of BC divides 200. We suspect that the order of BC is equal to 200. Right? That's at least, if things were nice, then this number that we wrote down actually is the order of the element. Right? But you have to sort of wonder, if I'm writing down random numbers, are they always the orders? Or could I write down some numbers very carefully so that one of these is actually not equal to the number that it's supposed to? Right? It's at least possible that I could find some set of numbers on some graph so that I could end up proving that some smaller power was equal to the identity. Right? And so that's sort of a basic question. Are these really the orders of the elements, or are they just numbers that the orders of the elements divide? Okay. All right. So now I want to do some examples. The first example I want to do is I want to talk about linear transformations, reflections as linear maps. And so let's start in the plane. So we're on the xy plane. And what I want to do is I just want to pick some vector alpha. And I want to write down R alpha. R alpha is a map from R2 to R2, sending alpha to its negative and fixing all points perpendicular to alpha. Right? Okay. So I'm going to go ahead and start introducing some colors. Let's go ahead and make alpha a particular color. So there's alpha. Here's the hyperplane perpendicular to alpha. right? It's the set of all points x such that x dot alpha equals 0. Right? Okay. So, what I want to know is if I give you some point x vector, I don't really need to name my coordinates, so maybe I won't. If I give some point x vector, where is this going to go? Actually, we could even pretend we're not in two-dimensional space because the formula is going to be the same. Where is this going to go under the reflection? The reflection is supposed to do this, right? It's supposed to fix the hyperplane, send alpha to its negative. And so what do I really want to do? I want to, the point needs to move in the alpha direction, and it needs to move the same distance on the other side, right? And so what I need is I need a formula for this distance. Well, that's sort of a classic problem. You've got some vector u, you've got some vector v, and you want to write down the projection of u in the v direction. And what do you know about this? You know that it's supposed to be equal to, let me switch back to white. The projection of u in the v direction is going to be some multiple of v. And the only question is what multiple, right? And this is simple enough that I like to just go ahead and redo it every time I talk about projections for my students, I tend to redo the proof because it's a simple proof, right? It's going to be a multiple of k. So even if you've seen this, it's a multiple of k. And what do we want? We want this to be an orthogonal angle, right? Well, what is this vector? This is end point minus start point. It's u minus kv, right? And we want kv dot u minus kv to be equal to 0. And so we want k v dot u minus k squared v dot v to be equal to 0. And then moving them to the both sides, it looks like this. Canceling out a k, it looks like that. And so the k needs to be v dot u over v dot v. Right? And so what we want is we want v dot u over v dot v, v. Right? Okay, so back over here. So what we do is we take the vector x and we're projecting it in the alpha direction, and then we're subtracting off twice of that. And so what's the formula here? So r alpha applied to some random point is what? It's going to be starting from that point, we want to subtract off twice the projection of x into the alpha direction. And so what we want is we want x minus 2 times, and what's this going to be? This is going to be x dot alpha over alpha dot alpha, alpha. Right? Okay. And now, so this is actually the formula for a reflection given by a vector of a hyperplane through the origin. Okay. That we take some random point and we subtract off 2 times x dot alpha over alpha dot alpha, alpha. All right. There's a couple of things that I want to do to this formula that make it a little bit, I should say, notice that this actually works perfectly well if instead of the situation we have there, we consider something in three-dimensional space. If we have, here's our origin, and here's our vector alpha, and we have some vector x, it's the same formula, right? Because again, we just project x into the alpha direction, that's the distance from the plane, and we're subtracting off twice. Right? And so this is not a planar formula, this is a completely general formula. Right? Okay. So I actually want to write it up here so that I can have it later. And the second model, so the first comment is that this works in all dimensions. This is the equation of a reflection through the origin in all dimensions. The second thing that I want to do is that I've been writing dot product because we've been using standard dot product. But very quickly, I want to use a different notion of dot product. I want to use something that's very like an inner product. I'll give you an exact definition. It'll be some sort of product that takes two vectors. It's some sort of product that takes a vector and gives back a number. Okay? Something like a dot product that takes two vectors and gives me a number. Okay? And so I want to replace dot product with some strange inner product. And so for now, I'm just going to write it like this. Okay, I just replaced the dot with this. Okay, for right now, think of this as standard dot product. But we're going to change it in a second. But the thing that I want you to notice is that suppose we had a strange definition of an inner product. I'll give you an example in just a second. But what is this going to do? Well, what I want to claim is that it's going to send, so suppose that I pick an alpha with only, I'm going to be in a vector space with some definition of this that I haven't told you yet. And the only property I want is I'm going to pick an alpha so that alpha is not 0. Okay? I'm going to pick a vector alpha so that alpha is not 0 for whatever definition I've put in here. And then I want to look to see what this does. So what does it do to alpha? If I replace x with alpha, what does it do? It sends it to minus alpha, even with a strange definition. Right? Because I'm going to get alpha minus 2, some non-zero number divided by the same non-zero number, alpha. And so this sends alpha to minus alpha. And when is it fixed? What points does it fix? When is this equal to x? When this is 0, exactly when that's 0. Right? And so if I have a strange definition and I use my strange definition to describe perpendicularity, suppose I call u and v orthogonal exactly when the strange definition gives me 0, then this is going to fix all the things perpendicular to alpha, even under the strange definition. Right? Okay. So, what this will describe, so if I come up with a strange definition that's kind of like dot product, but with slightly different properties, this will describe a linear transformation. This is going to be linear in both coordinates. So it's going to have a lot of the same properties as dot product. Okay? In particular, this will end up being a linear transformation. It'll be slightly strange, but it's still going to be a nice bilinear map. It'll be linear in the first coordinate, linear in the second coordinate. So if I had a linear combination, I can break it apart like I usually do. So this is going to be a bilinear map. Linear in the first coordinate, linear in the second coordinate. This will end up being a nice linear transformation. And the properties of this linear transformation is it's going to send alpha to minus alpha. It's going to send this point to that point. And whatever is perpendicular to alpha, it might be tipped, but whatever counts as perpendicular under this definition is going to be fixed. Okay? Let me actually give you a concrete example. Okay. And the concrete example define something like a dot product on R2 by the formula I want to think of u and v. I'm saying R2 because I actually have a fixed basis. Okay? I've got a fixed basis, and so my points have coordinates. Okay? So I want to describe things in coordinates, so I'm actually going to describe this using a matrix. Okay? So U and V, yeah, maybe I should put, I don't want to get too involved in the notations, but this is the coordinates of U. Actually, let me not put them there. Let me do it here. This is the coordinates of U in my fixed basis. Okay? I'm not done writing the formula, but that's what the square bracket means. Okay? So the square bracket means I'm not considering the vector, I'm considering the coordinates. And so if this is my vector U, then square bracket U in this case might be something like 1, 1. Okay? And I actually want to think of this, I want to think of the coordinates as a column vector. Okay? Or as an n by 1 matrix. Okay? So coordinates of vectors, so, all right. Coordinates of U in my fixed basis written as a column matrix. Okay, matrix with a single column. Because I want to describe my inner product, I want to describe the product that I'm interested in using matrix multiplication. Okay? And here's actually what I want to do. So I've got a 2 by 2 matrix in the middle. I've got a column, 2 by 1 column matrix here. And here I want to take the transpose. So here I'm going to think of it as a row matrix. Okay? All right. All right, so let's get some details up here. So in my coordinate system, here's how things go. So this is 1, this is 2, this is 3. This is 1, 2, 3. And so if I pick the point, like, if I pick this as U, then what is it? So there's a U. Let's pick a different one. Let's pick that as V. I just want to put some examples up here so that we're clear on what's going on. So what are the coordinates of U in my chosen basis? The column vector 1, 2. Right? What's V? Minus 1, 1. Right? And now, what's U dot V? Or the inner product of U and V? Well, it's going to be the transpose of U, the matrix 1 minus a half, 1, and then the column matrix for V, and this is going to end up giving us a number. Right? Let's go ahead and actually see what it is. So let's go ahead and just multiply the first two. So 1 minus 1, that's going to give me a 0. Minus a half plus 2 is 3 halves. And then 3 halves times minus 1, 1 is 0, 3 halves. And so this gives me 3 halves. Okay? So the dot product ends up giving me 3 halves. Okay. Next comment is that actually, if the kinds of multiplications that I'm interested in, are multiplications of the form from a vector space from a vector space cross itself to R, and I'm going to be interested in the ones that are defined just like this in the following sense, that they're going to take U and V and they're going to define to be the coordinates of U transpose some matrix, coordinates of V. And the flexibility I want is that M is some arbitrary real symmetric matrix. Okay, this is an example. Right? They're real numbers and it's symmetric. It's equal to its transpose. Those are the kinds of things I want to look at. What properties do they have? The first property that I want you to note is that because I required it to be symmetric, this is actually a symmetric product. That the product of U and V is the same as the product of V and U. Because what happens when you do it in the other order? Well, when you do it in the other order, transpose M U, but M is actually equal to M transpose. And when you take the transpose of a product of matrices, it's actually the transposes in the reverse order. And transpose is the same. And so this was some real number, but the transpose of a real number is the same as the real number. And so this is the same as UV. Right? So it really is a nice symmetric product. Okay? Second comment is that if you stick the identity matrix in the middle, then what do you get? If you put the identity matrix, you just get standard dot product. Right? Because the identity matrix times any vector is just the inner vector, and so what you're getting is you're getting U transpose V dot multiplied, and when you multiply, you just see an ordinary dot product. And so this is a generalization of standard dot product where you're putting something other than the identity matrix in the middle. Okay. All right. So, what I want to do now is I want to look at the reflection from R2 to R2. I want to look at the reflection defined by this alpha. So what do I mean? I've got my alpha. So that's my alpha, E1, standard basis vector. But now, rather than using standard dot product, I want to use this. Okay?
Should that be positive then?
Not necessarily. Yeah. And that's why it's not really, when people define the notion of an inner product, some people require this to be a positive definite matrix. So after you do a change of basis, it really looks like standard dot product. Yeah, let me actually say it that way. If the matrix M is positive definite, then you can do a change of basis so that it looks like standard dot product. If M is not positive definite, there is no change of basis to make it look like standard dot product. But we want the extra flexibility. Okay? All right. This particular one turns out to be positive definite. Okay? And in fact, we can prove it's positive definite because you know the nice fact about how to check matrices being positive definite. How do you check? You just take determinants of principal minors. Well, the 1 by 1 minor is positive. The 2 by 2 minor, 1 plus a fourth, it's positive. This is a positive definite matrix. Right? Okay. All right, but let's go ahead and do this. So I want to use this formula to write down a linear transformation. So the first thing we need is we need to figure out what the hyperplane is for alpha. What are the set of vectors x such that the inner product of x and alpha is 0? Right? So let's go ahead and do this. We can do this. Let's just figure out what this equation means. So x is going to have some coordinates. And when we take the coordinates of x, so we want the coordinates of x transpose 1 minus a half, 1. And the coordinates of alpha, actually we can write down coordinates of alpha, right? What are the coordinates of alpha? 1, 0, because I actually picked a basis vector, right? And we want this to be equal to 0. This we don't know what it is. It's some sort of x1, x2, right? We don't really know what the coordinates are. And so we just want to solve this equation. Well, let's go ahead and multiply these two together first because that's easier. And so we get that times that is 1, that times that is negative a half, right? And so what do we have? We have x1 minus a half x2 equals 0. And so x1 equals a half x2, 2x1 equals x2, something like that. So this is first coordinate. Second coordinate, so what does this look like? If you think of these as x and y, this says y equals 2x, right? Y equals 2x. It's a line with slope 2. And this is saying that the things perpendicular to alpha look like that. Right? According to this product, those vectors are perpendicular to this vector. Right? Because we've changed this basically changes our notion of length and angle. This is how we're going to think of length and angle. We're going to use length and angle using this formula. Take all your ordinary formulas for lengths and angles using dot products, just replace this wherever you see a dot product. And so what's the length of a vector? Well, it's going to end up being the square root of u dot u. Done this way. Okay? And etc. You just use it for all your formulas for lengths and angles. So these are the things, so this turns out in this product, this is perpendicular to this. Okay? So what's this linear transformation? What does it do to a point here? Let me actually pick a particular point. So the point 1, 1. What does it do? Well, we know that it sends alpha to minus alpha, and we know that it leaves these fixed. Right? Because of the way we said it, right? All the things that are perpendicular to alpha are fixed. And alpha goes to minus alpha. And so this is fixed. Also, which direction do points move? It starts at x, and then it moves some scalar multiple of alpha. Right? And what was this coefficient here? That's actually measuring what multiple of alpha it takes to get back to perpendicular. And so that coefficient right there is actually measuring this. And when you subtract off 2, so where's this going to go? It's going to go there, because that distance is the same as that distance. Right? It moves in the alpha direction, and it's the same distance away. Okay? That this is a scalar multiple of alpha, and this is minus that scalar multiple of alpha. Yeah?
Can you clear that distance is equal as symmetry?
What's that?
Hasn't the distance changed, so we have to...
But if you calculate it, one thing about this, if you use this for the distance, when you use that for the distance, then whatever scalar multiple of alpha this is minus the scalar multiple of alpha. Yeah? Okay. So actually, as soon as I tell you alpha and I tell you the hyperplane, without the formula, you can still visually check where things move. Right? And so if I said, where does this point move? Well, you just say, it's moving in that direction, and it's going to go this, it's going to go there. Okay? So the vector and the hyperplane actually allow you to see where things go. Okay? Let's do another one. Let's do beta. Beta is going to be there. And so actually most of our calculations are going to be similar. So I'm going to reuse them. So what's h beta going to be? H beta is going to be the set of all points such that x dot beta is equal to 0. What's the only thing I have to change? Instead of using E1, I'm now using E2. Instead of using 1, 0, I now just use 0, 1. Instead of selecting out the first column, right, because that's what this did, selected out the first column, it's now going to select out the second column. And when we select out that second column, what are we going to get? We're going to get minus a half x1 plus x2 equals 0. And so x2 equals 1 half x1, or if you want to think back in terms of x and y, this says that y equals a half x. And so it's the line of slope a half. Okay? So, line of slope a half, it's going to look like this. Right? That's h beta. Yeah? Okay. So, what I want to do now is, I want to look at the orbit of alpha under RE1 and RE2. So these are reflections. I mean, in sort of a slightly strange sense. They're fixing a hyperplane, they're sending a vector to its negative. I should have said, what happens if I do RE1 twice? What if I do R alpha twice? In full generality, with any definition of this product, what happens if I do it twice? It's going to be the identity, because all the things perpendicular are fixed the first time, they're fixed the second time. Alpha gets sent to minus alpha gets sent back to alpha. And then I'm fixing this stuff perpendicular to alpha, I'm fixing alpha, and if you think about it for a second, the stuff perpendicular to alpha is dimension 1 less than the whole space. And so this is an n minus 1 dimensional space. Alpha is over here. I chose alpha so that the denominator is not 0. Because alpha dot alpha is not 0, that means that the vector alpha is not in H alpha, which ends up meaning that H alpha and alpha span the entire space. And so if I fix all of H alpha and I fix alpha, I fix the line determined by alpha, I determine the space determined by H alpha and alpha, I fix everything. Okay? So in full generality, this is a linear transformation of order 2. Okay? No matter what the definition is of the product, this is order 2. Which means that RE1 and RE2 are going to generate a dihedral group. This is something of order 2, this is something of order 2. And so I can look at applying RE1. Let's give them simpler names. How about we call them R and S? Is that okay? So let's simplify this. Let's call this R. Let's call this S. Just so I don't have to keep saying RE1, RE2. So I want to apply R, I want to apply S, and then R, and then S, then R, and then S, and then R, and then S, and just see what happens. Right? And because we have this visual way of doing this, we no longer need the formula. We can do this in the picture. Right? Okay, so let's start here. So this is the identity, and then I want to apply, which one's which? Let's apply R. Where does it go under R? That's the yellow one. Under R, goes to here. right? Now let's apply S. S is the red one. And so it's going to go down here, right? Because this is a half, right? So it goes down there. Now let's apply, well, if we applied S again, we'd come back. And so we got to alternate in order to keep going, right? And so I do R, I do S, now let's do R again. It's going to go to there. Okay, now S. It's going to go up to there. Now R. Now S. We end up back. Right? And so what did we do? We actually went to there, we 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 went to there. And this actually looks like sort of a slanted hexagon. Right? And in fact, if I start thinking of the unit vectors, what is this describing? This is describing, if you think of this, we said this was positive definite, right? Because we calculated the two determinants, we said this was positive definite. Because it's positive definite, it describes an arrangement of two vectors in space with ordinary dot product. And what does it say? It says that I've got a unit vector, I have a unit vector, and what does the negative a half tell me? That this matrix can be interpreted as describing a pair of vectors in space. Since the diagonals are 1, they're both unit vectors. Because the dot product is minus a half, if I tried to construct these in a standard dot product, I would need to make a 2 pi over 3 angle. Right? Because dot products of unit vectors are their cosine. And so this is telling me that the cosine is minus a half, which is telling me that the angle is 2 pi over 3. And so rather than doing this picture, I could actually do standard space and pick two vectors with a 2 pi over 3 angle. And then everything that we did here could actually be mimicked over here with regular reflections. And what would you see? You'd see, let's go ahead and do this. So we've got a yellow reflection, and that's perpendicular because we're doing standard dot product. And we've got the red vector, looks like this. And what you should recognize here is that this looks like our ordinary sort of marking off a fundamental domain. And if I took a point here, I was using green before, and I started looking at, now we're talking about the reflections on two sides of a fundamental domain, and we know that R and S raised to the third power gives us the identity, because R times S is going to be a 2 pi over 3 rotation. And if you actually followed the image of a point under these, it would go over to there, and then it would come down here. Oops, let's see, where would it go? This is steeper. It's going to be right. Okay. Yeah, I think I need to go ahead and put in the third hyperplane. Anyway, it's going to be our old picture. It's going to be our old picture, and everything's going to work, right? And so what I want you to realize is that this is actually our old picture just in a new basis. It's our old picture in a new basis, and in this basis, it no longer looks like standard dot product, it now looks like this. But everything else still works. Everything else still works. Okay? In particular, if I use the matrix 1, 1, cosine pi minus pi over m, as my m to define my inner product, then RE1, RE2, raised to the nth power is the identity. Okay? Because RE1, because what I've described then is I've described two vectors that in the standard picture have a pi minus pi over m angle between them, which means that the two reflections, when you reflect between those two reflections, you're going to get a 2 pi over m rotation. And not only that, but m is the order of RE1, RE2. Right? Because I actually know what this looks like in standard coordinates. That if I do this picture using this dot product, this kind of product, everything that happens in this picture is exactly the same but slightly distorted as what happens in the standard picture where I've got two vectors with a pi minus pi over m angle between them. And I know that two vectors in standard picture with pi minus pi over m angle between them, there is an angle of pi minus pi over m between the reflection hyperplanes, which means that their product is a 2 pi over m rotation, which means not only is this equal to the identity, but it means that there is no smaller exponent equal to the identity. Right? Because their product in standard coordinates is a 2 pi over m rotation. In order for it to be the identity, I have to raise it all the way to the nth power. This is the smallest integer. Yeah? Okay. Where am I going next? Racer. Okay. Okay. Let me actually leave that example up and let me okay. So what I want to do, I want to actually use our example that we have there from earlier. So I want to write down a 4 by 4 m. And what I want to do is I want to write down 1, 1, 1, 1. And so this is sort of corresponding to A, B, C, and D. And then what I want to do is I want to write down, let's see, A and B. Over here we had AB to the 29th is equal to 1. Right? So what I'm going to do is in this spot, I'm going to write down cosine of pi minus pi over 29. Okay? And here I'm going to write down cosine of pi minus pi over 29. And, well, what am I going to do with this? Let me not write the rest of the matrix yet. Let me go ahead and talk about what I'm going to use this for. And then I'm going to consider R4 where the product is given by U transpose M V, where it's this M. Okay? I'll fill in the rest of this in a second. And then consider the subgroup of GL4R generated by RE1, RE2, RE3, RE4. RE1, RE2, RE3, RE4 represent the four standard basis vectors for R4, but they're linear transformations defined by this formula, where that inner product is this inner product. Okay? So, before we go any further, what can you tell me about RE1? This is going to be some map from R4 to R4 from this formula. It's going to have order 2, right? Because this formula always describes something of order 2. Right? Actually, in order to even define this, what did I need? I needed the denominator to be not 0. So we should probably check that first. What is E1 dot E1 in this formula? Well, it's going to be 1, 0, 0, 0, 1, 0, 0, 0. And so what is that doing? This is selecting out the first column. This is selecting out the first row. And so it's selecting out the first row and column. It's selecting out the number 1. And so in that, so if I use that matrix to define my product, E1 is a unit vector. Right? E1 is a unit vector. That's what this is telling me. Because this is E1 dot E1. This is E2 dot E2, E3 dot E3, E4 dot E4. And so all of those are unit vectors. In particular, none of them have 0 length. And so this formula always makes sense for these 4 particular linear transformations. Right? The formulas work for these 4. And so that's an order 2, that's a linear transformation of 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 order 2. Okay? And maybe I could even give them names. Let's call that A, B, C, D. What's going to be the order of AB? Well, if I'm only looking at A and B, if I'm only looking at RE1 and RE2, so now I have to do something with 4-dimensional space that we can't visualize. We've got 4-dimensional space, and I've got E1, right? What's RE1 going to do? It's going to send E1 to its negative, and it's going to fix the perpendicular space, perpendicular with respect to this, whatever that means. And so it's going to fix some 3-dimensional subspace, right? And since E1 is not perpendicular to itself, E1 dot E1 is not 0, it doesn't contain this 3-dimensional. So it's this and some 3-dimensional space, probably at an angle, like in the other example. Okay? So it's going to fix this, and then it's going to move this to that. In particular, every point that moves in the E1 direction. Right? Because what are we doing? We're taking our point, and we're adding or subtracting a multiple of E1. Everything's moving in the E1 direction. That's the only motion that takes place under this. Right? What about with RE2? Similar statement. We have E2 going to negative E2, some strange 3-dimensional perpendicular subspace that's fixed, and every point that moves in the E2 direction. Right? In particular, as I start multiplying by E1 and RE1 and RE2, when I multiply by RE1, points move in the E1 direction. When I multiply by RE2, it moves in the E2 direction. Then it moves in the E1 direction. Then it moves in the E2 direction. But it's only moving in the E1, E2 directions. And so everything stays in the plane that it was in originally, the E1, E2 plane that it was in originally. If it's in the E1, E2 plane, it stays in the E1, E2 plane. If it's up here, it's going to stay up here. Okay? There's some 2-dimensional plane that it stays in. All right. And what's fixed by both? The things fixed by the first one are some 3-dimensional subspace. The things fixed by RE2 is going to be some other 3-dimensional subspace. Their intersection is going to be some 2-dimensional subspace. Codimension 1, intersections codimension 2. And the motions are all happening like this. And so actually, what I want to claim is that if it's fixing a codimension 2 subspace, if you just check what's happening in the E1, E2 plane, when that gets back to the identity, everything's fixed. But if you look at, if the E1, E2 plane gets back to the identity, then the E1, E2 plane is fixed, the intersection of the 2 hyperplanes is fixed, and so these 2 dimensions are fixed, these other 2 dimensions are fixed, their span is going to be the whole thing. That's the only thing you have to check. You have to check that they really are linearly independent, but their span is going to be the whole thing. And so once the E1, E2 plane becomes fixed, everything's fixed. Okay? So you only have to check what happens on the E1, E2 plane. But when you look look at just the E1, E2 plane, you're down to this picture. Right? When you're looking at points in the E1, E2 plane, this is the only part of M that matters. And so what's happening on the E1, E2 plane? On the E1, E2 plane, it looks like in standard coordinates a pi over 229 angle. And so on the E1, E2 plane, the product is going to be, in standard coordinates, look like a 2 pi over 29 rotation. Which means that the 29th power will be the identity, and that is the smallest power that's equal to the identity. Okay? All right. So, I think you can kind of guess how I'm going to fill out the rest of the chart. Right? Because what am I going to put in the next spot? In the 1, 3 spot, I'm going to put cosine pi minus pi over 12, cosine pi minus pi over 11. What I'm going to put down here, I'm going to make it symmetric. And then here, this is BC, cosine pi minus pi over 200, cosine, is that the Google? Yeah, that's Google. Pi minus pi over 10 to the 100, and cosine pi minus pi over, what one's left? 14. Right? And then same thing on the bottom. And what do I actually have? What I actually have now so these 4 linear transformations, R4 to R4, have the following properties. RE1 squared equals RE2 squared equals RE3 squared equals RE4 squared equals 1. They're all order 2, just by the way the formula works. RE1, RE2 to the 29th equals 1. And this is the order of RE1, RE2. That there is no smaller power equal to 1. Right? Dot, dot for all the other relations. Right? So, if I let this over here, if I call that W, what have I now shown? What you should now see is that these 4 linear transformations inside GL4R satisfy all of those relations. Right? I found 4 linear transformations that square to the identity, that where the first 2 have a product of the 29th power equal to 1, where the first and the third have the 12th power equal to 1, where the first and the fourth have the 11th power equal to 1, second and the third have the 200th power equal to 1, second and fourth, Google's power equals equal to 1, and the third and the fourth, 14th power is equal to 1. Which means that the map, I probably shouldn't have erased this part. Oh well. Which means the function sending A to RE1, B to RE2, C to RE3, and D to RE4, where these live inside W and these live inside GL4R, extends to a group homomorphism not onto. Because this is defined by relations, and the images of the generators satisfy the relations. Right? Now, suppose I had a group, suppose I had A and B in a group and I sent it over to H by some group homomorphism. And I knew that AB to the 200th was equal to 1, but I didn't know whether that was the order. But suppose in the image I look at phi of A, phi of B, and I know that that the order of this is 200. That tells me the order back here had to have been 200. Because if the order was smaller, there would be a relation that it satisfied, and the image would satisfy that relation. Right? And so this is sort of an indirect way of proving that the orders really are what we think they are. That we know from the diagram, from the definition, from the presentation, we know that the order of BC divides what we wrote down. Now what we've found is a systematic way, because even if you'd given me different numbers, I could have written down a different M for matrix. Or it's, well, there's different, this term gets used for other things as well. But it's sometimes called the Coxeter matrix. But it's used to define what's called a bilinear form. And from that bilinear form, we've now defined a linear representation. Right? And very explicit one. That from the diagram, you can immediately write down this real symmetric matrix. From that real symmetric matrix, you define something that's a strange kind of dot product. From that strange kind of dot product, you can write down reflections. From the reflections in the basis vectors, you actually get some reflections that satisfy all the relations of the Coxeter group. Okay? Which means that there's always a map from W over to linear transformations of, if this is a n-generated Coxeter group, it'll be GLNR. Okay? The next thing that I want to say is that this is not quite the end of the story, but this is the beginning of of proving the basic facts. Just the existence of the representation, like I said, and knowing what it does on 2x2 blocks, knowing that the 2x2 blocks really do look like rotations of planes, is enough to tell us that this group, the order really is 12, the order really is 11, the order really is 10 to the 100. The order really is 200, right? And so that's already good information. And I guess just to conclude with a little bit of history, so I've given you various historical dates. I've got them written down. Should I write them down? I still have 10 minutes. Well, let me just say them orally. So I gave you some dates with regular polytopes. When we were doing the regular polytopes, I said there was a Swiss mathematician, Schläfli, that studied the regular polytopes back in the 1880s, way early. Coxeter worked on regular polytopes and actually classified the spherical reflection groups, the discrete spherical reflection groups that are now called spherical Coxeter groups. He classified them in the 1930s. Okay? But he was very young when he did that. He actually he was born in 1907, and he only died in 2003. I mean, he lived till fairly recently. Okay? But in 1934, he actually classified the discrete groups generated by reflections. So that was one family of mathematics. Then we also talked about Lie theory. Sophus Lie, I looked him up, he's Norwegian. That's the kind of Scandinavian he is. He's Norwegian. He was in the 1870s when he did his work on defining continuous transformation groups. Wilhelm Killing was a German in the 1880s. Gave a classification of what are called complex semi-simple Lie groups and Lie algebras, essentially alluding to the Lincoln diagrams, but he didn't use the diagrams. But his proof was very hand-wavy and not very good. In the 1900s, in his dissertation, Élie Cartan, the French mathematician, gave a nice rigorous proof that this was the nice list, the A tilde, B tilde, C tilde, D tilde, the ones that end up corresponding to the Euclidean reflection groups. Lots more work on Lie groups, some more work on regular polytopes, and then in the 1960s, Jacques Tietz, who's a Belgian mathematician, in an early paper, he was also very young at the time. In 1961, he wrote down a general definition of a Coxeter group. Okay? He wrote down this idea, taking a random diagram, writing down a random presentation. And he did this in 1961. When he wrote that down, one of the first things that anybody would ask once you do that is, this is just a presentation. Is it clear that you can do anything with it? Do you understand these groups at all? And so in that same first paper, he defined this and he defined this. Okay? And so at the point where he defined general Coxeter groups, he also defined this representation. So that you at least knew this idea, that the orders are exactly what you think they are. And so there really does exist a group where this is order 29, that's order 200, etc. No matter what numbers you write down, there's a group with those orders. And in this very first paper in 1961, he proved something more, and this is what really got people kind of excited about this entire family of groups. What he actually proves is that this injects. That this is a faithful representation. And because it's a faithful representation, now you actually know how to do a word problem. Because if you have a word in your generators, you turn them over into matrices, right? Each generator corresponds to one of these REIs, and you can actually, because that's a linear transformation, you can write it down as an actual matrix in the basis. And so to check whether a word is equal to 1, then you actually just multiply the matrices. But he also did more. He actually analyzed what things looked like over here and came up, what we're going to do is there's actually going to be geometry similar to the now we have things that look like reflections. We have vectors, we have hyperplanes, and we can start looking for something that looks like our fundamental chamber and start reflecting it. And then we can say we're moving from our fundamental chamber over to some other fundamental chamber, and we can look to see whether, as we move step by step by step by step, we'll end up seeing the Cayley graph in the geometry, and we'll be able to see shortest paths. We'll say, is there ever a hyperplane that I cross twice? And if there's a hyperplane that I cross twice, then I can reflect through that hyperplane and shorten the word. The entire picture that we drew last time with the G2 tilde, where I said, we crossed this hyperplane twice, and so just reflect the path. We now do it here with this strange notion of inner product, because we still have hyperplanes, and we still have fundamental chambers, and everything still works. And so the entire geometry of spherical and Euclidean Coxeter groups generalizes to an arbitrary diagram in this way. Okay? And so that's actually what I want to focus on from here on, and I'll go ahead and finish a few minutes early. But that's how you use linear representations. They were present right at the birth of Coxeter groups, and the existence of this linear representation give you the solution to the word problem, give you that the orders are exactly what you want, and it's the way that you can get started proving facts about Coxeter groups, and shows that there are nice, rich, interesting families of examples. Okay?